Today I'm a little bit in a not in a slightly, quite different setup, as you might see right here. Um, um, yeah, I want to talk a little bit about this. How do I say? I think I mentioned about in my second video about the things related to Clebsch-Gordon problem and how do we find um, direct sum decomposition into irreducible components of tensor products of representations. Uh, I think before starting, I should be doing some kind of sanity things related to sort of I don't know. I By now I forgot the exact name, but anyway, it's something like any representation can be broke down into reducible components. Um, I think there should be some kind of um, conditions that makes it possible. Obviously, like it doesn't feel like it should work by itself. Uh, that representation should be decomposed into irreducible parts by being just representations. What else? Yes, so today I want to talk about slightly about this young tableau tricks to solve a Clebsch-Gordon problem. I mean, I think Clebsch-Gordon problem is a more general statement than what I'm trying to do here, in a sense that uh, I think I might be mistaken. I might be not completely accurate in a sense that, for example, uh, probably in some cases you are interested in finding the explicit isomorphism. I'm not really sure. Uh, because I'm interested in how this Young diagram and Young tableau magic solves the problems arising from how do we decompose tensor products of, for example, irreducible representations into uh, direct sum of irreducible parts. Which for SL2 case, I think it is a little bit easier in a sense that you can just sort of construct uh, the how do I say it? Like the SL2 case, we have irreducible representations as just the symmetric powers, powers of the standard representation, right? And if so, what is the yeah? Uh, for example, what is the direct sum decomposition of a symmetric power of m and symmetric power of n? Well, I mean the tensor product of them, and this can be just dealt with some kind of. I mean, the exact solution I think involves sort of how do I say it? Like you have to do with the composition of representation, and if you just consider it, and you should get the answer. And I mean, since I already been thinking about it and did some homework for this particular video, uh, or how do we explicitly do it for using Young diagrams and Young Tableau approach, which is purely combinatoric or algebraic. Um, it just feels like I mean I think I had a slightly different view about the Clebsch-Gordon problem for SL2 before dealing with um, it using the formulations of Young tableaus and combinatorial approach. So I think uh, I have talked enough. So probably it's time to get started. Um, this video is probably gonna be a little bit shaky in a sense that I will not probably do everything in detail. I mean, uh, not because it is not an educated sort of omission, but just okay. I will just tell you what I did. I just looked it up. Looked at. I was studying using uh, Fulton's representation theory because it was. I mean, it is very visual, and I like the approach itself, and I was just solving the some kind of exercise so to explicitly find the direct sum decomposition of symmetric power m and symmetric power n for SL2 case, and yeah, after that I got interested in, okay, we know the answer for SL2 case, so but what happens for SL3 or SLN, and what happened is I asked, of course, Gemini. I mean, this Google ChatGPT thing, because I wanted to know what happens if we just generalize it to SLN case, and it gave me the answer. I don't know when I asked, but anyways, it gave me an answer that it is sort of related to Young diagrams. So what I did is I just had a very long discussion with Gemini so far uh, to arrive at the at sort of pseudo understanding, I would say, of what's happening. Uh, and I just want to talk about this because I think it is somehow connected to my second video um, about this abstract nonsense of rotating groups and so on in a very surprising way to me. Uh, so let's get started a bit. And what I'm gonna do is lay out some kind of foundations. I think the first one that we need to talk about is a Schur-Weil duality. Is it? I don't know how to pronounce it. I hope it's Weil is the correct pronunciation. It is something like 1 second. I will just copy paste from Wikipedia. So, oh no, the statement is quite large, and what I'm gonna do is just to write for how much. Let's suppose I'm doing it 3 times. Decomposes into direct sum decomposition of representation. D. I'll tell you what D is in just a moment. This is a representation of GLN n, and this is the representation of symmetric group of one second. I need to be careful. Yeah, n, right? Is it n? Okay, whatever. Some kind of symmetric group representation. So I just had a look at it, and well, Gemini claimed that from this we can deduce sort of the relationship of a Young diagram and representations. Like this is somehow sort of counting the possible Young diagrams in a sort of combinatorial way. Like there the explicit rule of doing it is a Littlewood Richardson algorithm, which we impose something like if we have something the standard, we have a sort of standard representation as a box as a Young diagram, then we ask how can you append this to it. By appending, I mean we cannot just arbitrarily append it to form some kind of a random, not even a skew tableau. So what happens specifically in this case is we have two kind of possible ways. Like I mean, I did this is incorrect way of doing it, but I mean this is one way of doing it. This is the second way of doing it, and yeah, this is this is sort of how you this is the first condition of how to construct like this is the first condition that you need to somehow follow during the construction of sort of allowed Young diagrams. And the second part is something called Yamanouchi word, I think, word condition, or whatever, so some kind of condition that that tells you something like if you count like this, like not count but read in the wait, is it? No, it's like this. If you read from the top row to bottom row from right to left, not left to right, then you should always have something like sort of increasing condition. Is it strict? I don't think so. And so on. And the reason that we are imposing this, I guess, is this Yamanouchi word condition imposes some kind of sort of well definedness, in a sense that there are some allowed operations when we construct this, and Yamanouchi word imposes something like I think it's in fact something like that. You the skew tableau that we are getting can be rectified in a very specific form. The specific form, I think it's something like the first row consists of 1, 2, and so on and so on. Of course, this is greater than 1. I think this is the reason why Yamanouchi condition is needed. Like by this I mean the number of row elements, and so on and so on. I mean the Yamanouchi word condition, I think, gives us sort of guarantee that we can construct, we can rectify in this format. I don't fully grasp the reasoning behind it, in a sense that, for example, I think I read in Fulton's a Young Tableau book that there are several possible rectifications. I mean, for standard tableaus, I think it's unique. By I don't know how to pronounce it, but Judetaki, something like that. I mean, this algorithm of rectifying the skew tableau. Okay, what do we have? Yeah, this is sort of this part is a sort of Littlewood Richardson part. And I think we need to talk a little bit more about the Schur-Weil duality. So the Schur-Weil duality part is about is a little bit more general than what we need. For example, to be honest, I don't at the current moment I don't really care about the general linear group case, because I mean I'm dealing with the algebras. So what I've been thinking is how will I make this guy into a statement of Lie algebra? Well, I mean, which is somehow pretty obvious in a sense that what we can do, like this is representation, right? And there is a obviously the associated Lie algebra, and we just take the tangent the tangent space identity, and it will descend into general linear Lie algebra from general linear group. And then what's gonna happen is basically this statement descends to the statement about the algebra. And what else? Yeah, so I've been solving some interesting things. So something like, the exercises that I'll be talking about from now on is generated by Gemini. I don't know if it appears in a very in some specific sources, but I can imagine that it appears pretty much everywhere if it deals with Littlewood Richardson rules application for solving some sort of isomorphism problem of a Clebsch-Gordon problem. For example, let's say V is a standard representation of some kind of SLN, and we want to find the following. This is tensor product, so it is not necessarily guaranteed to be sort of irreducible by itself. I mean, at the current state, I think it is probably going to be right, or no, probably not. For us, yeah, I don't think it's gonna be. But anyway, this is represented in for some magical reasons that I asked Gemini for several times, but I mean, it Gemini presented enough evidence to make me believe this. Yeah. And so what happens now is we just use the sure while duality for here. Uh, so now when I need to talk how to construct this sort of allow the Young diagrams, and let's see. So this is represented by one box. This is represented by another box, and when we try to do sort of a tensor product, we just label one of them and try to append it using Littlewood Richardson rule. So what we have is something like this. This is one type of allowed one, allowed append, and we have direct sum. This thing. Now only what we only need to do is to look at this. Like in a sense that to which irreducible representations it corresponds to. Oh wait, but it's just one tensor power. This is sort of trivial in a sense that it is symmetric, and this is alternating. I might have chosen too trivial one. Like it is a linear algebra, linear algebra fact, right? for the tensor product O itself, how it decomposes into symmetric and antisymmetric parts. Okay, then I will solve the sort of second part, which is pretty much still a bit trivial in some sense, but not necessarily too trivial. I think it's something like we want to find this thingy, and I think I want to do it in a very specific Lie algebra. I think it was SL3 or SL2. I think it was SL3. So what this one is a box. Right. Where did I write down the exercises? I cannot find it. I should have written down in some other notebook. So this is represented by this one, and this is represented by. But is it? I think it's for SL2 case only. Or is it? No, shouldn't be. Shouldn't be. I will consult the. Whatever. So we label the first row as 1, the second row as 2, and we take the tensor power, which is just saying how do we append this. We need like we cannot put 2 here because it will violate the Yamanouchi word condition. And then we need to put 1 here, 2 here. and we cannot put 2 here because we will again violate Yamanouchi word condition. Then okay, we have one part, 1 2 1 2. For SL3, this is basically this one, which is just trivial. Yeah, and this one I will leave it as it is. So for SL3 we know this thing. I mean, for if it were to be SLN, I'm sorry. I'm a little bit skeptical about this part, but whatever. Is it? Is it to conquer? I'm not really sure. But I mean, suppose this is some kind of W that is represented by this one. I'll cheat a bit and let it be like this. Then I can. But this stays for SL3 case. Yeah. And what else do we have? And the next exercise that we wanted to solve is I need to see if it's well aligned. Okay, I think it should be visible. Yeah. I'm currently in my parents' house, and my setup is a bit different from the usual one. Let's be lambda correspond to this thing. So this is lambda, and the mu correspond to this thing. It is still a very similar setup in some sense, but what I find it to be interesting is that so what Gemini suggested, actually, when you consider this thingy, just always enumerate the second Young diagram and try to append to the first. Like this is the algorithm that he suggested. And when I was doing it, I wasn't so sure about it. So what I did is I just used this obvious isomorphism. This is a little bit stupid one, but anyways, I tried to append this thing to make sure that it is somehow well-defined thing, and verify that my calculation is indeed correct. So yeah, let's try to append it, following the rules of a Littlewood Richardson algorithm. So okay, let's see what we are allowed to do. We still have a very so to say trivial situations, and not in direct sum of this thing 1 2. First of all, if you cannot flip it, because there are two rules. Like it needs to be a semi-standard young tableau. It is not young tableau by itself, but anyways. But is it? Like I think Queen just remove this one, and this is semi-standard by itself, and it is the rectified tableau. Like the rectification is pretty obvious. This is outer corner, and we can just remove it, and this is inner corner, right? Yeah, I think it's an inner corner after removing this one. What else? Yeah. So what we have is we have partition 3, 1 here, and this is 2, 1, 1. Partition, yeah, partition of like Young diagram is a partition of some integer, right? Positive integer, obviously. Yeah, so this is one way, and we have second way. Yeah, we did this one. We are now appending 1, 1 to this thing. Let's first consider what is allowed and what is not allowed. Let's say I appended 1, 1. This is certainly allowed according to semi-standardness, like weakly increasing along the rows. And the Yamanouchi word condition is obviously satisfied because the only non-empty entries are ones. And you might be tempted to create something like this, but this is not allowed because semi-standard Young tableau should increase strictly along the column, and one is not strictly greater than itself. So I will just cross it out. Then we have we might have this one and this one. Yeah, this is semi-standard, right? Or is it? Yeah, I think Juliet King pushes this thing right side, and it rectifies to sort of standard. I might be abusing a little bit the language in a sense that, I mean, by sort of standard rectified thing. It is probably incorrect term, but I don't know the exact term of this correctly rectified young tableau. I think another for the same reason. This thing is not valid, like because the column doesn't strictly increase. And what we got is 3, 1 direct sum 2, 1, 1 partition. So actually the answers that we got matches to each other, which should match due to tensor product commutativity. What I found interesting is some kind of connection to sort of Grothendieck group. From now on, it's a little bit of speculation. So I mean, this is a neat trick that I still plan to explain in a relatively more detailed way. Because I did it, but it's more like I don't know the boundary of this argument, so to say. Like for SLN, it's two kind of special linear groups to expect it to work for any other Lie algebra. Like I can imagine that it's gonna work for nice Lie algebras. Yeah, and what else? I think I wanted to do quick remark on the parallel of it to growth and degrowth. So the problem is that so we actually get how it decomposes into direct sum, right? Uh, a very good question for me was like, to be honest, I didn't care, but um, the Gemini gave me as as the final exercise uh, compute the explicit isomorphisms. Not for all of them, like it could have asked me, but find a computer explicit isomorphism for Clebsch-Gordon problem. I think physicists are interested in this. I'm not really sure, but I mean, I just saw recently a meme on a thread or X about this uh, an excerpt about Clebsch-Gordon coefficient problem uh, that interested me because I saw the word, the name Clebsch-Gordon, and I was like, oh, this is Clebsch-Gordon. I might be interested in. And then, yeah, I looked at it and I was like, what the hell is going on? Like, it is a very. Mm, it looked very painful for me. Not gonna lie. Like this is fun. It feels a little bit like toy, but it is fun. But the Clebsch-Gordon coefficient calculations that I saw didn't look so fun. So when I was looking at this, I realized, oh, this is very strange, in a sense that I couldn't mm, sort of think about how do we actually get like the transition matrix, like this how tensor products uh, decompose into direct sum of something. And if you have direct sum, then it is something like I might be tilting some algebraist, but anyway, like we can write in some kind of coordinate, right? And uh, uh, because we have coordinate, we should be able to write sort of like in a matrix format how it transitions. It's a linear algebra after all. And yeah, what I found is this Young diagram magic probably doesn't tell you how this transition actually happens. And when I and Gemini explicitly said that you can't do it using Young diagram alone. Specifically, this type of formulation. And I was very interested uh, because it ring the bell a lot. I think the previous from the previous video, uh, you might remember, or I will just recall slightly. Like it just feels like it's a Grothendieck group. Like when we do Grothendieck group of some abelian category, you just consider not modules, but you just consider modules to be abstracted into some kind of module class, module iso class, which have some kind of exact sequence uh, exact sequence to have some kind of relations, having something like, if is it something like M A B is M A plus B class or something like this. Uh, yeah. And what else? And I think we were computing a lot of things during the course of this category of course. Uh, like we were interested in finding the how projectors look like. It is a slight misconception to say that we actually computed the explicit uh, explicit coefficients of uh, on the basis of it of the projective whatever, it decomposes into simple basis, right, or whatever. And what I found parallel is something like when we do this, we actually lose a lot of information here. That modules and the morphisms of modules have. And yeah, what I found interesting is just this one might be just parallel of this. So when we construct Young diagram, and we use just a Young diagram to compute what is isomorphic to, it is definitely a lot stronger, right? Or is it? For Grothendieck group, if we have iso classes, can we decompose? Yeah, decompose, and we have sort of a series of exact sequences. I think there might be some abstract nonsense reasoning, and probably this Young diagram construction is a special case of Grothendieck group. I'm not completely sure. Because to be honest, I don't believe Gemini in a full faith. I just believe what I understand, and it just feels a lot like that. This Young diagram construction is a special case in which we have this nice Clebsch-Gordon problem case that we only need to count Young diagrams. I might be waving a hand too much, but I will try to formalize my current these arguments in later videos. I'm currently on a trip, and it's it's a 5 a.m. Local time. I'm not in Germany currently, and the time zone discrepancy is killing me a bit. That's my sleep schedule is completely off. But yeah, I've been thinking about this for a while. Like, I really wanted to learn about this topic, and when I found out about this, when I was solving and having a long chat or course of this discussions with Gemini, I realized, holy, this has always been about Grothendieck groups, and I wasn't thankful enough when the professor of the course of category O introduced the Grothendieck group. Like, for me, it felt like, oh, why do you care about this thing? And when I see this, holy, if I didn't know about Grothendieck group and just did this, I think this a Young diagram thing might have been just something like sort of entertainment. Like, I see the beauty of combinatorial and algebraic reasoning, but still, for some reason, when I see when I see the name Grothendieck, I definitely feel more like it's a sort of structural reasoning than the combinatorial, some kind of. I mean, combinatorial is the nature of this part, I guess. But anyway, this might have been a very cool coincidence if I didn't see or know about this one. I guess my my current video is going to be a pretty ill organized one. But yeah, I think I told you enough that I what I wanted to say. Um, it's a very kind of raw because I didn't have enough time to sort of organize it. Let me be honest, I didn't organize my first videos, but this is sort of exceptionally sort of raw content. It didn't age well as of now, uh, and yeah, I just wanted to talk about this one. And in yeah, I'm currently in my parents' home, and I found. I think by now you have noticed. You probably have noticed that I like writing in fountain pens from my beautiful collection of sort of practical fountain pen collection. And yeah, I was searching for this specific ink for ages. I was yeah. I thought I threw this away. It's a Waterman. Uh, if my sources are correct, specifically Gemini, then this Waterman should be true Königsblau, and the problem with existing Königsblau that I was using so far is that uh, they are a little bit dry. Like when I was writing in this pen, this is a platinum Japan, EF nib. Holy, it's quite scratchy usually, and um, this isn't scratchy that much, because I'm traveling with this diamond, um, which is somehow lubricates it well. But I was having trouble using Parker Quink, or I think I tried the. Did I try something else? What I mean, this Pelican Solamis are designed for European, European fountain pen, which are quite wet by itself. And by the way, yeah, this is by the way currently has Waterman loaded in. The I'm not really sure if you can see it on video, but the color is slightly different. It is very similar to Parkour Quink, but I just feel like I finally have an ink that can be erasable and pretty well lubricated in some sense. So yeah, I I think I might switch into it. Whatever. Yeah. By the way, does anybody know like this? Is this expired or not? Or does it expire at all? Because I'm not really sure for how long it was here, and to be honest, I'm not even sure if I closed it well. It's a little bit dusty because I was out of my parents' home and didn't touch my ink collection for at least 1 year, because I was using Supernote and other tablet or writing on screen methods, which is kind of a little bit shame for you, I guess, because probably this is less visible Yeah, I suspect that this video might not be uploaded to YouTube because it's 5 a.m. and I'm probably out of my mind, and I'm yapping about all the things. So yeah, I wanted to talk about this cool thing, cool abstract nonsense that, in the specific case of Clutch Gordon, has very beautiful, in my opinion, parallel. And now I think about Grothendie groups in a more mm, the Grothendie groups are useful than it looked like. I mean, when I got introduced, it just looked like a complete categorical nonsense. But mm, when I see the connection, it just looks like, oh, this isn't so bad. Right, when you try a new field, you probably think about uh, mm, and probably pretty much any culture has something that smells bad, but when you taste it, it isn't that bad. And I think this categorical nonsense and gluttony groups were sort of smelling bad things for me for a very long time. Like I knew that it is abstracting away and lets you see more general stuff, but mm, using this connection, I think I appreciate Grothendieck group nonsense a little bit more. And that's it for today.